All right, everyone. So if you're here for Apply Track, thank you very much for coming. We greatly appreciate you showing up. This week, we'll be doing our standard format. Right now, the plan is if you are on the CNN's notebook, we're going to be having you in the middle here. If you're still finishing up on any of the beginner or the MNIST notebook, feel free to sit over there. And then finally, if you finish the CNN notebook, we're going to be, if you need help on the RNN notebook, we'll be going over there. This week our attendance code is I'm at a loss. As always, you guys know the deal, asset cluster, join our Discord, all that. Specifically, we'd like to highlight that we've updated the asset cluster a little bit. So it's going to include the slides and recordings. So, if you want to review some of what we've talked about in past meetings, feel free to do that there. And also, this week, we are having another reading group. We love to plug it, but this one is really cool. This is all about mechanistic interpretability, understanding transformer circuits. It's basically, transformers are doing a lot of fancy stuff. And how do we figure out exactly what they're doing? Because they can be a little bit of a black box. And also, for theory track, if you're interested at all, we'll be talking next week about embeddings, which is how we represent words for machine learning. Long short-term memory, how we remember sequential data, transformers and attention, and large language models. Now, if none of those words make sense to you, perfect. Come to theory track. If they do make sense, but you want a refresher, also come to theory track. And as always, Mondays 6 to 8, Kaplan A65. You guys know the drill. And this is the roadmap. Halfway there. And as always, any suggestions, hit us with them. All right, so now we're going to talk a little bit about loss functions. Who's that? Which person did this? That's you. Okay, yeah. Hand it over to Wade.
Okay. All right. Anyway, so as I was gonna say Jordan, geez, Jackson, as Jackson said, I'm not going to be talking about loss functions, but first we have to introduce a statistical method called maximum likelihood estimation. It's basically a method of finding parameters to best fit a data set given an assumed distribution. So we assume that our data follows say a normal distribution. We then we'll find an optimal theta to best fit the data set. We covered this in theory track as well, and we have more slides as well in there as well. So if you go to the asset cluster, you can find that. But beyond that, it's basically just how a machine learning model makes predictions given the data we put in. It's just MLE. So that gets into what a loss function is. So it basically tells us how far away from the optimal input we are. And if we have a higher loss, we're doing worse, is basically what a loss function models. And so, the other thing to note is that we take the derivative with respect to the gradients of our model to basically see how much to modify the weights. And so this is really what's happened. This is how we get our gradients. So we take the derivative with respect to, we take the derivative of the cost function. So how much is the loss function changing with respect to each weight? We nudge it according to gradient descent. And so, and why do you think the loss function must be differentiable? Because obviously, if you can't take the derivative, you can't get any sort of gradient descent because gradient. So examples of loss functions include cross-entropy loss, mean squared error, and cosine similarity. And so softmax, what about softmax though? Softmax is the multinomial approach to the problem. So rather than setting t of y to y, we basically do what's this? We do this kind of formula here. So t of 1 is equal to 1, 0, 0, 0, 0, 1, t2, 0, 1, 0, 0, 0, so on and so forth. And then And then finally, T of K is just the zero vector. And so all that we're doing is we're fitting the previous approach, but for a multi-class problem. So the probability distribution, it's not Bernoulli anymore. It's not a simple binary this or that or whatever. So softmax is really just kind of a continuation of that for multiple classes. And if this will work. Okay, there we go. So, and then we can't use, so to handle this output nonlinearity, where we don't have like a discrete, like it could be either right or wrong, but the way we do it is to get some sort of like continuity with it, we get some probabilities. So we essentially, we take our output layer, we apply softmax, and what that yields is a series of probabilities. So this is the probability that it's in class 1. This is the probability that it's in class 2, so on and so forth. And then we'll take the maximum of that. And so cross-entropy loss is really just applying negative log likelihood after inputting your lodges into a softmax and getting your probabilities. So this is kind of the loss function that we use for these kinds of models. And so it yields some interesting results, as it says here. So the derivative calculation of the loss function with respect to the input lodges is it's equivalent to the true labels, one hot encoded, minus the actual outputs, which will ultimately give us a much simpler gradient calculation. And as we know, that's obviously really important. And so weirdly, many machine learning frameworks have softmax included with cross-entropy, even though, as we just saw, they're not actually the same thing. So cross-entropy describes the loss, whereas softmax is just the activation function. But because they're used together so much, it kind of makes sense to include them together. And finally, here's the implementation of cross-entropy loss and an MLE through in the okay, there we go. Basically, here's the code. Some of you guys might find this helpful in your on your notebooks if you have any trouble. So as we see here, we don't have softmax is not included here, but guess what? It's already included. So that's my spiel on loss functions. Now we're going to be moving on to regularization. What? Okay. All right. And so Artine's going to handle that. Artine.
Whoa. So regularization. Yeah. So to recap what overfitting is, overfitting is when we do really good on our training data, but that means since we did so good on our training, that actually hurts our performance when we are given a new example in our validation loss. So if you look here, if you don't train and don't do too well in examples in training, you're gonna have a really high training loss, and then your validation, the unseen data it's not trained on, will also have a very high loss. And if you train too well on that data, and you can kind of see it's overfitting, it's going through as many as it can, it makes it so when you give it a new data point, let's say like here, it's going to be way higher, way more off. Versus what you really want is the case where it trains pretty good on the training data, but it still has the ability to generalize to unseen data like your validation. So in this case, with a polynomial, this one would probably do best. So one technique to improve this is called dropout. Dropout, you essentially drop out or kill parts of the network randomly at training. So a normal number to use is 0.5. So this means pick 50% of the neurons in the network and just kill them. The idea here is making it so the network can't necessarily overfit, because let's say it tried to memorize an example or something, or like rely on one part of the network to do something. What would happen is next time it wouldn't be able to use that part. So it has to rely on another part. And this kind of making it so different parts of the networks have a bit of redundancy and that kind of thing, make it so it can never do really well in the training. But that means that inference, when you turn on all the neurons back here, you actually allow it to learn very well, because it didn't overfit, and it's still able to generalize because its neurons still learn something, but they didn't learn specific examples. So this is kind of similar to, I'm not sure if we talked about this, but ensembling. This is like, imagine you created 3 separate networks, right? And then what you did is you take, you don't even need a meta classifier. You just took an average of these 3 networks, right? So the idea is that since each of these learned different features from different data, they each kind of account for each other's strengths and weaknesses, right? In the case of a classifier, like this one can be really good at doing cats and dogs, but not like, I don't know, birds. This one can be good at birds and not cats and dogs, right? So the idea is that they all average together. Their final prediction is better than just one. And you can kind of think about dropout as doing an ensembling inside of the actual network. Because when you're deactivating some of these neurons, right? Let's say you had some input features that you passed in the network down here, some of them would actually just be turned off. And that means it's limited to a subset of the data, meaning this part, like this structure of the network here, could only learn like those specific, learn how to account for these specific traits that aren't blocked at the input, right? So you're essentially inside of the network creating a bunch of these like mini networks you could think of. And then when you actually comes time to, I'll go back to this image, when it comes time to actually run the model at inference, you re-enable all the neurons, and it's as if you are averaging a bunch of different networks, right? So that's kind of the reason we do dropout. And in practice, this is just a little implementation detail. You normally want to divide by the probability of dropout. The reason why is, let's say you normally have 50%. When you sum these two, it might be, let's say, 1, right? And that might be how much it should be activated by. But when you re-enable everything, if your ratio of dropping out was like 50%, all the neurons will now have 2 times the saturation, which they never had at training. So what you do is you just normalize it by the probability. So you scale it so that training and testing, the neurons saturate the same amount. Again, this is just implementation detail. If we actually look at PyTorch, if you used just like any other layer, you just add a nn.dropout layer, and you put the probability of neurons dropping out, and it handles that for you. If you actually look in the dropout right there, it does. Show my mouse? Yeah. It does the 1 minus p. It scales for that, so you don't have to worry about anything. To implement, you literally just put a neural network.dropout, the same way you'd put neural network.linear in a layer, and it will go to that layer, and it will pretty much just mask out or deactivate those at that certain layer, like right there. And then remember that when we're actually calling, when we want to test on our validation or test data set, what we want to do is we want to call our model.eval. And what model.eval does is makes it so this dropout doesn't happen, right? It goes to the entire network and re-enables everything, right? So when we call model.eval, it turns off dropout. It makes it so, okay, we're not dropping out this layer, which is dropping out neurons. It's pretty much just gotten rid of. And then also just another thing, it doesn't store the gradients. So remember, our weights have also values which are gradient, which is how much it's changed by. We store that so we can forward pass and backwards pass and back propagation. But when we're actually just running through to predict an image or to classify a single image, it's pretty much useless to have the gradients, or again, we want to disable dropout. So we call model.eval when we want to go test our model. And then when we want to train the model, remember to turn model.train to call model.train method, because that then re-enables dropout and then also turns back the gradients. So your model can like actually learn. Yeah, so if you actually look, this is kind of cool. This is dropout like this is a little slide, just dropout works. It's empirically, even if you don't know the theory, maybe you're not agreeing with, in practice, dropout does help a lot in deep neural nets, and just leads to better performance, because again, that maybe the idea of ensembling these other things, but empirically does very well. Again, here, it forces it to learn distinct features in the network at different parts. And it doesn't allow it to overfit to a single instance example, right? Because each of these features might have been just learning how to classify like a single image from the train. By disabling and re-enabling parts of it, you prevent it from doing this overfitting, and it actually allows it to do better on test data, which is what we really care about. We don't care if we can classify the images we know how to classify. We care if we can classify the images which we have never seen before. That's why we care about dropout, because it's a regularization technique that helps with test accuracy. And a quick shout out to ACM in 2020. They wrote a little Medium article on dropout that I found while like putting together these slides, and they have these memes in it. So it's kind of funny. Use dropout. This option doesn't exist because p equals 0.5. Very funny, very funny. Oh, and then last thing. This is just another thing you can do for regularization. It's called data augmentation. So you can, given like, let's say you have one image in your data set or one example, you can pretty much create new synthetic data from those images. So let's say this is your original image, right? It's a dog. Let's say you have two, like a dog and a cat. What you can do, instead of just saying, this is an image of a dog, classified as a dog, or an image as a cat, classified as a cat, you can actually blend like alpha values, like transparency, and create a dog cat label where it says predict 0.5 dog, 0.5 cat. And it's literally like, do you see how it's like a transparent kind of mix between? And this actually helps. It helps the model better generalize, because again, it's giving you just more data to train off of. And there's some other ones like, what is this? Is this cutout, I think? Yeah, wait, let me move this. Oh, this is cutout. Yeah, this is cutout, where they literally cut out a piece of the image. And what this does is it makes it so it can't, let's say, rely on just the face of the dog to predict it's a dog. It makes it so it has to rely on other features like, oh, it has a fluffy tail and it has these paws here, right? So again, in our training data, if we just had dogs like this, where it's always the face, the problem is, let's say you get to an image later where it just has like the paw or tail of a dog, it's probably not gonna be able to classify that because it might be relying heavily on the face. So cutout is actually a really good technique, because what it does is it makes it so the model has to learn to attend to different features, and it can't just rely on one. Again, this is what we really want from regularization techniques and data augmentation. It's kind of to make it so maybe it doesn't do as well at training. Maybe it's harder for it to classify this in training. It will be, but when it's given a new unseen image, it's actually able to generalize and understand better. And this is another one, cut mix. That's interesting. That's funny. It's like a cat dog. But yeah, that's pretty much it.
That's normalization. So, just to start, I'm going to give you guys some issues with training deep neural networks. Even with batch normalization, you'll have these issues, but just in general, one of the issues is called the vanishing gradient problem. As your neural network gets deeper and deeper and deeper, you guys remember when last applied track we talked about how the gradients you use chain rule to calculate the gradients. So as a network gets deeper and deeper and deeper, those gradients add up and eventually decrease, especially if the values of those gradients are less than 1. And so, this issue occurs, and you can't properly train deeper networks. Another issue is parameter initialization. So in this case, for example, let's say you initialize all your parameters to be 0, right? And in that case, all the parameters might learn the same information, and they might go in the same direction, which is bad for training because you want variability with your parameters, right? So parameter initialization is also a really important aspect of training deep neural networks, and it's pretty hard, honestly. Can you guys think of, for example, one bad parameter initialization technique, or one bad, like, let's say, what range of numbers, for example, like 0 or 1, 0 or 5 would be bad? You gotta think about it. feel free to. Just to give you guys like a quick example, for example, if I initialize my parameters to be really large, for example, if my weights have like, you know, all of their values are from 50 until 100, for example, that would be really, really bad because our gradients would explode really quickly because the updates to those weights would also be really large, right? So that, for example, is a bad parameter initialization. Another thing that I want to mention, it's variable learning rates, right? So you guys remember last time when we had the equation for weight update, we had something called a learning rate, right? And a learning rate, for your model to converge, your learning rate has to change. It has to get smaller and smaller and smaller and smaller as you get closer to that minima. And for deeper neural networks, you have to have lower learning rates because they're susceptible to small changes in your learning rates, right? It makes sense because you have more weights, you have more complexity. And these are some of the issues that batch normalization tries to tackle, right? This technique originally came out in a paper by Sergey Loffe and Christian Szigeti. I hope I said their names correctly. And it sought to fix a problem called internal covariance shift, right? And these days, a lot of people say that it doesn't actually solve this problem because of the technicalities, but it's so important to mention. What is internal covariance shift, right? Every single time you train your model, the internal distribution of the model between the layers change, right? Suppose, for example, you have some hidden layer and you have another hidden layer after it, right? The values of that hidden layer, the output, are going to be the input of your next layer, right? But every time you update the weights, what happens? What will happen is the distribution of the activations between these weights change. So your model has to relearn that complexity. And that's, that leads to slower training times, right? And so how can we change this? What can we do so that this problem can be fixed? Oh, fine. Ignore the batch normalization. So we use batch normalization, right? What we effectively do is we take all of our activations over a batch, and we get the mean and the variance, and we normalize them. So that the variance is 1 and the mean is 0, right? Do you guys know what normalization is? As you guys have like some info about statistics. If you guys want to know more about normalization, you can come to me after and we can talk about that. But that's effectively what we do, is we just normalize it so that the activations have a mean of 0 and a variance of 1. And ignore that for a moment. And then after that, we have two trainable parameters called gamma and beta. We use those to shift our activations. And this helps in many different ways. One is it improves stabilization because now the activations from one layer to another layer are normalized, right? So none of those values are extreme. Everything follows a good distribution. In addition to that, it increases the speed of training. In fact, in the original paper, the author stated that training was improved by around 14 training steps, right? Which is drastic. And almost all machine learning architectures today use batch normalization. And it also improves gradient flow, again, because your values are normalized, so the gradients are more likely to be within a certain range. They're not going to get too small, they're not going to get too big. And it also has regularization effects, and it helps you generalize your model to different values. And so different validation instances. And so this is the basic gist of batch normalization. We just take suppose we have a mini batch, we just take the mean of that mini batch, then we take the variance of that mini batch, and we normalize them, right? And afterwards we scale and shift. And if you guys are wondering why we scale and shift, the main reason why we scale and shift is because it adds flexibility to your model, right? Because if we only had their mean and variance be 0 and 1 all the time, then that model wouldn't be complex enough because some training instances and some data sets might have different distributions between their layers. And so this is basically the flow that we have for batch normalization. And this is an example of batch norm. So in this case, you'd use batch norm 2D. One good place that you'd use it is for convolutions, right? That's where you'd use batch norm 2D because now we're taking the activations with respect to the features rather than sort of like a one-dimensional vector case. In the other case, you just use batch norm. So this is batch norm 2D, and all that this means without learnable parameters when we're setting affine to false, is all that we're doing is we're just saying we want gamma and beta to be set, because gamma and beta are the only learnable parameters we have. And to end it, if you guys are wondering, what do we do during inference stage? Because, I told you guys we use the mean and variance of your batches. We use the running mean and variance of your batches. During inference, we use the preset exponential moving average of your mean and variance. So we just use that. And if you guys don't know what an exponential moving average is, again, come after and I'll explain to you what it is. And yep, we can just, while we explain the Safari 10 notebook, we'll give you guys a demo on what CrossEntropy is and also how to use batch norm. You guys have any questions?
Yeah, all right. That pretty much concludes the quick little talk that we have here at the beginning. I mean, you guys know the drill. Just to reiterate for any late joiners, we're gonna try and have the CNN notebook be in the middle here. If you're still working on MNIST or the introduction notebook, feel free to go over there. And then finally, if you're on to RNNs, feel free to go over there. And yeah, just have at it. We'll be coming around. If you have, any questions, comments, concerns, flag one of us down. And, thank you guys for coming.